So in this video we're going to be looking at conditional probability. So the first thing we look at is the notation. Now to use the notation for conditional probability, all we do is we draw a vertical line between two elements, and this says the probability that A happens given that B has happened. So we'd read that as the probability of A given B. In a Venn diagram, this situation can be modelled by saying, right, I've got B shaded in there. The probability that A happens given that B's happened is that little red bit, so it's the intersection part. So we can say that the probability of A given B happening is the probability of A intersection B divided by the probability of B. Okay, and that bit I highlighted there is called the intersection, so the bit between the two, and that notation, that upside down U, means intersection. So in a tree diagram, we can represent it as well. So I have got A and not A, so the little dash meaning not A, and B and not B. And if you think about the notation that I'm writing on the tree diagram here, you can see that although it looks a bit odd, the probability of B given A happening, well, we know A's happened and then we're doing B and so on. So think about why that notation is what it is. But if I want to then say that, right, the probability of B, of A happening given B has happened, okay, well, we know if B has happened, we must have either gone that route or that route. So because B has happened, and only one of them is the route that A's happened on. So a way of thinking about this one is that I put arrows and stars, and the conditional probability is the starred route divided by the arrowed route. And then if I use the notation that's on my tree diagram, you get a slightly more complicated formula. It's exactly the same thing actually. You're writing the same thing as previously, but it's written out in a more mathematical way. Okay, the top bit is simply the probability of A intersection B, and the bottom bit is simply the probability of B happening. Okay, and this is actually known as Bayes' theorem. So an example here. Okay, so we talk about trains in a station and whether they're big trains or small trains or so and so on. So read the question and then have a look at how I'm solving this one. So we're going to do it two ways. First of all, using Bayes' theorem. So the basic probabilities that we got, we're going to identify. So we're going to say the probability of S is that we get a seat. F is that it's the probability of getting a four carriage train. And E is the probability of getting an 8 carriage train. So identifying those variables just makes it a little bit easier for following through with the workings as we need them. So Bayes' theorem, we want to find the probability that we get a seat, given we've got a seat that we're on an 8-seat train. Okay, so using that, writing out the theorem as we had previously. And then we're going to think about what are the values that we're going to have that goes in there. So let's just run through those ones. So the probability that we get a seat on an 8-seater train is 0.85, and the probability that we get a seat on a 4-seater is 0.65. Probability of an 8-seater is 0.25. The probability of a 4-seater is 0.75. So substituting our numbers into this, type it in the calculator, and going to get an answer and give it to 4 significant figures. Exactly the same question, this time with a tree diagram. So here's my tree diagram. I've already drawn it out. So we've got 8-seaters, 4-seaters, and the various probabilities that we need, whether we get a seat or we don't get a seat. Now let's identify what the routes are going to be that we'll be using. So we're saying we're getting a seat, so we've either gone that way or that way, and the one on the 8-seater is the starred one at the top. So we're saying we're going to take the starred route, which is a quarter times 0.85, divided by the arrowed routes. So it's the quarter times 0.85, what we had before, plus 3/4 times 0.65. And obviously we get the same answer. Okay, another question. Got 3 machines which are making clasps. Okay, so we can use a tree diagram. We've got machines X, Y, and Z, and the probabilities of getting either one of those machines 0.6, 0.3, and 0.1. And then the clasps are either faulty or they're not faulty. So again, the little dash meaning not faulty. And we can put our probabilities given each machine in there as we see it. Now the probability it's faulty. Okay, well if it's faulty, it's either gone that way, or that way. So using the rules of tree diagrams, multiplying along the branches and adding them all together. And we get our answer of 0.031. Now we want to find out the probability that it's a defective class, but it's come from machine Y. So the only route is that there was starred one in the middle. So we want the starred route over the arrowed route. Well, the starred route is 0.3 times 0.02, and the arrowed route was what we worked out in the previous bit of the question. And again, answers to 4 significant figures. If I did the same question using Bayes' theorem, just for part 2, for part 1, we wouldn't use Bayes' theorem for that one. There's nothing conditional about part 1. So writing out our formula this time. And then it's a case of just thinking about from the question, what are my numbers that go into there? And clearly when I work it out, I get the same answer.